In the first chapter, we are going to revisit some of the topics you might have learned in high school. It's not linear algebra proper, at least not the version of linear algebra we'll be talking about in this course in 1341, but I think it's a good place to start. I'm going to present some information, which, as I said, is hopefully something you have seen before. If you have not seen this stuff before, it will be important to pay particular attention, but also presumably to try out some of the exercise questions so that you can bring yourself up to speed. One of the major themes of linear algebra is that there's a lot of things we know how to do in 2 dimensions, 3 dimensions potentially, that we would like to be able to generalize to higher dimensions, to n-dimensional space. When we study complex numbers and we look at high school geometry, it is going to give us a source of ideas that we may then attempt to generalize to higher dimensions. That's sort of the idea of studying these sort of older things that you've known for a while. You could argue, as some people do, that algebra, not linear algebra, just algebra in general, is the study of solutions of polynomial equations. And we start with linear systems, the simplest ones, and eventually it brings us to things like field extensions and Galois theory, right? So it's a lot of that can be quite sophisticated. This isn't what we're going to be talking about in this course, obviously. Linear algebra, then that would be the study of solutions of linear equations, which is to say very simple polynomials. We might have multiple variables, multiple equations, but all of the equations we have are linear in their variables. Complex numbers, first sort of thing we'll study, very interesting in its own right. But it does have applications, right? It's called complex numbers, imaginary numbers, but they're not not real. They exist, they're there, and they do have honest to goodness applications, in particular for people who study engineering and physics. Where did complex numbers come from? Well, eventually we'll see that I, the standard complex number, is a solution of the quadratic equation x squared plus 1 is equal to 0. But historically, this isn't where complex numbers came from. Historically, people knew what to do with x squared plus 1 is equal to 0. They would say, well, this quadratic equation has no solution. When they tried to come up with formulas that would be very like the quadratic formula for degree 2 polynomials, but when they tried to come up with formulas for degree 3 polynomials, they had formulas that, that worked some of the time. But in order for the formula to work, you sometimes had to compute the square root of a negative number. In its own right, that's not something that existed. There's no real number that's the square root of a negative number. And that was sort of problematic because we're using this formula. It gives us the right answer, but there's this weird thing in between where we have to compute the square root of a negative number. It gave us the right answer because some of the terms canceled out one another, and all of the terms that included square root of negative numbers would disappear. And so people say, well, we're using this formula. Something's weird about it, but we can still use it. And so we will because it gives us the right answer. But we don't know why it works because it shouldn't, because we're using square roots of negative numbers. That's where these things came from. And then eventually we realized, well, now that we have a bit of an idea as to how square roots of negative numbers work, let's see if we can come up with algebra on these special types of numbers. So once we look at something like x squared plus 1 equals 0 and we know that it has no solution, well, we can say we know it has no solution because the graph of, say, x squared plus 1 a function would not cross the x-axis. Right? You'd end up with something that looks like this. Because it doesn't cross the x-axis, then there's no solution. And that's a reasonable way to look at things. If you take that point of view, you can also say that an equation like x plus 1 equals 0 would have no solution, right? Because in order to have a solution to x plus 1 equals 0, you would need a negative number. And a negative number, at least in ancient times, didn't represent a quantity. I can't look out the window and say there is minus 1 cow in the field right now. So we sort of invented negative numbers so that we'd be able to solve all of the equations that look like x plus 1 equals 0. The x minus 1 equals 0, we knew how to solve it. We just get x equals 1, and we were happy with this as a solution. Cubic equations, at least assuming that all of the coefficients are real numbers, they always have at least one real solution, right? If you draw the graph of any cubic, it's going to look like, well, potentially something like this. There's always going to be this one point where there is a solution. So we knew there was always a solution. The formula that we were using, as I mentioned, I'm not writing it down here because it's too complicated for our purposes, but the formula always gave us at least one of these solutions. There could be more than one, right? You can imagine a setup where what you have instead is something like this, and there are in fact 3 solutions, but there was at least always one, and we knew how to find it with the formula, but we were working with imaginary numbers. So we're gonna do the same thing we did when we were trying to solve equations like x plus 1 equals 0, which is to say, well, x equals minus 1 doesn't really exist, but we'll invent it as a number. Assuming that the invention that we do, has nice properties and it isn't weird, it's something we can do. You can't just invent a number and say, now there's a number called potato. That's not the way it works. But if you can invent a number called potato and it behaves with respect to all of the other pre-existing numbers in a reasonable way, if a lot of the rules you had are satisfied, then it makes sense to sort of add that potato number to your list of existing numbers. So we did something like this for the imaginary numbers. We called one of the solutions of x squared plus 1 equals 0 I standing for imaginary. That, in retrospect, perhaps was a poor choice. Imaginary doesn't mean that it doesn't exist. It's another name. And in real terms, what it means is that the axis is the vertical axis. So we think of real numbers as being on a horizontal axis and imaginary numbers as being on a vertical axis. In which case, imaginary doesn't mean does not exist. It just means at a 90-degree angle from the real numbers. This number I has the property that when you square it, you get minus 1. And we know that no real number has this property because the square of any real number is non-negative. If you use this notation, then you can write the square root of a negative number as the square root of the absolute value of the negative number times I. That's the definition, if you want, of the square root of a negative number. So if we have the square root of minus 9, that would be, well, minus 9 is the a, the negative number underneath the square root. And so that would be the absolute value of minus 9, which is 9 times the square root of minus 1 times I. And so the square root of minus 9 would be 3i, 3 times I. But you can also write 9 as the square root of 81, right? We know that. 9 squared is 81. So 9 is the square root of 81. And you can write 81 as minus 9 times minus 9. And then if you had Well, if you remember, in high school, you learned that if you have the square root of a product, that is the product of the square roots, right? This rule right here. You might be tempted to say, well, the square root of minus 9 times minus 9 should be the square root of minus 9 times the square root of minus 9. And if that's the case, well, we know what the square root of minus 9 is. We just computed it. It's 3i. The second square root of minus 9, also 3i. 3i times 3i, technically that should be the same thing as 9 times I squared. And we know what I squared is. I squared, according to this rule here, is minus 1. So then we end up with minus 9. And that tells us that 9 is equal to minus 9. And we know that's impossible, right? It's impossible because that rule that tells you that the square root of AB is equal to the square root of A times the square root of B, that is a rule that only applies when A and B are, well, I wrote strictly positive here, but non-negative would have worked just as well, right? By adding I to our list of numbers, we have found that this rule does not apply to all of the real numbers. It only applies when A and B are both non-negative numbers. So sometimes when you add new numbers to your list of numbers and they satisfy some of the properties, you're happy, but the price you have to pay is that certain properties do not hold anymore, or at least they don't hold in that general case. As a convention, if you pick a random real number A and you square it and you take its square root, we are going to say that the value of this is the absolute value of A. It's always going to be a non-negative number. What we're saying is that when we write this, we only mean one of the square roots, not necessarily the other one, right? The square roots of 81 would be 9 and minus 9. When I write the square root of 81, I mean specifically 9. When I write the square root of 81, I mean specifically 9. If I want minus 9, I will specify it by writing the negative sign in front of it. That's a convention, and we could have picked the other convention. We could have said the square root of any number here is minus the absolute value, but we chose to stick with the positive value of it. Now, we know how to solve quadratic equations in general. We have a quadratic formula. You remember it. It is minus b plus or minus the square root of b squared minus 4ac divided by 2a, assuming, of course, that your quadratic polynomial is ax squared plus bx plus c in the first place, right? So how do we find the solutions, say, of x squared plus 4x plus 8 equals 0? There's two possible roots. We use the formula, in this case, a is equal to 1, b is 4, and c is 8. So we just plug in the numbers. Minus b plus or minus the square root of b squared minus 4ac divided by 2a. And by actually working out the expressions, you end up with minus 2 plus or minus 2i. Okay? How do we get this? Like if you divide each of the terms in the sum by the denominator, minus 4 divided by 2 becomes minus 2, and then 6 minus 32, that's minus 16. So that second term is 1 over 2 times the square root of minus 16, and then we write square root of minus 16 as the square root of 16 times I. Square root of 16 is 4. 4 divided by 2 gives you 2, and then you end up with minus 2 plus or minus 2i. Again, if you know how to do this, that's great. If you're not sure how to do this and how to get this result, you need to get on it. You need to practice until you're able to do these simple manipulations without breaking a sweat. How do we verify if the answer makes sense? Well, we can take one of the square roots, or one of the roots, I should say, of the quadratic polynomial there. Let's take minus 2 plus 2i. You plug it back into the original equation. So take this thing here, plug it back in here, and you'll get minus 2 plus 2i squared plus 4 times minus 2 plus 2i plus 8. Here's something to be weary of. Minus 2 plus 2i, all of that squared. You need to recognize what this means. It does not mean that you take the first and you square it, and you take the last term and you square it. That is not enough, right? There's something else that needs to come in here as well. Write it out fully. Minus 2 plus 2i squared is minus 2 plus 2i times minus 2 plus 2i. And then if you do the product, I believe in English you use the acronym FOIL. First, outside, inside, last. Right? So you take the first terms, minus 2 times minus 2. Then you have minus 2 times 2i. Then you have 2i times minus 2. And finally, you have 2i times 2i. Let me just put it fully here as 2i times 2i. And then you simplify this. It is going to become 4 minus 4i minus 4i plus 4i squared. You use the multiplication rule to get this thing. The second bit was 4 times minus 2 plus 2i. Well, we can do the distribution here. That gives you minus 8 plus 8i, and finally plus 8. Put all the terms together, all the terms that have i's together, all the terms that have i's squared together, all the terms that have no i's together, until you get to, well, 4 plus 4i squared. And then we remember, by definition, I squared is a shortcut for minus 1. So we put that in here, and we get 4 plus 4 times minus 1, 4 minus 4, which is 0. You can do the other root similarly. Again, if this is something you can do naturally, that's great. If this is something you have a bit of a hard time with, you need to practice. We are expecting that you know how to manipulate monomials and binomials and these types of polynomials in general.